Hello everyone, my name is Danny Abu Jawde and I am happy to present to you my joint ACC paper with Pierre-Loic Garrosh and Mazen Farhoud. To start, we are interested in computing state invariant sets for the uncertain system G delta shown. Namely, the uncertain system is formed from the interconnection of a nominal system G and an uncertainty operator delta that is assumed to lie in a pre-specified set delta. The nominal system G is assumed to be a stable, discrete time, linear time invariant system. To compute the sought invariant sets, we will combine the integral quadratic constraints IQC approach with the well-known S procedure. In particular, we will be using the notion of a pointwise IQC to characterize the uncertainty set of interest. A pointwise IQC is defined similarly to a standard IQC with the added requirement that each term in the infinite summation is non-negative. As for the disturbance input, it will be assumed to lie in a pre-specified set at each time step. The main contribution of this work is a novel combination of the IQC approach to robustness analysis with the S procedure for the computation of state invariant sets for uncertain systems. A second contribution is that we allow for a pointwise characterization of the disturbance input. This is in contrast to standard approaches in robust control, where the disturbance input is assumed to be a finite energy signal in L2. Finally, a nice feature of the proposed approach is that it is flexible and provides a template to be extended to modified settings. Consider the uncertain system G delta shown. The equations of the nominal system G are shown where K denotes the discrete time step, xg of K denotes the state vector at time K, D denotes the exogenous input, and theta and phi are internal signals. The uncertainty operator delta is assumed to be causal and bounded and to lie within a pre-specified set delta. From the figure, we have that theta is equal to delta phi, thus closing the loop. The disturbance input dk at time step k is assumed to lie in a convex, closed, and bounded polytope denoted by gamma. Accordingly, we define the set d gamma as the set of vector-valued sequences d such that dk is in gamma for all k. We are now ready to formulate the problem of interest. Namely, we want to find a positive definite matrix Q and the associated ellipsoid EQ such that if xg0 is in EQ, then xgk is in EQ for all time steps k, uncertainty operators delta and delta, and disturbance inputs d in d gamma. We will now define the notion of a pointwise IQC as it is used along with the S procedure for deriving the results in this paper. But first, we will recall the definition of a standard IQC. Let Psi be a stable system and S be a symmetric matrix of appropriate dimensions. Then the set delta is said to satisfy the IQC defined by Psi and S if the summation from k equal to 0 to infinity of Rk transpose Srk is non-negative, where R is the output of the filter Psi driven by phi and theta is equal to delta phi. The state equations of the filter are shown, and we note that the initial condition xc0 is equal to 0. Now, the set delta is said to satisfy the pointwise IQC defined by Psi and S if Rk transpose Srk is non-negative for all k. That is, we are requiring the term inside the summation on the previous slide to be non-negative for all time steps. Clearly, if a set delta satisfies a given pointwise IQC, then it also satisfies the corresponding standard IQC. However, the converse is not necessarily true. To derive our results, we need to form an augmented system H that combines the equations of G and Psi and maps theta and D to R. The relevant equations, as well as a representation of system H, are shown, where the uncertainty operator delta is highlighted in brown on purpose, as it does not enter into the definition of system H, but rather a constraint is enforced on the filter output R instead. The realization of system H is shown, and its state vector xh is defined as the concatenation of the state vectors of systems G and C. We will now state the main theorem in the paper. Consider the uncertain system G delta. If the set delta satisfies the pointwise IQC defined by Psi and S, and there exists a positive definite matrix P and non-negative scalars tau1 and tau2 such that the following inequality holds for all d hat in gamma, then if xh is in the ellipsoid defined by P at time k equal to 0, that is, xh0 transpose P xh0 is less than or equal to 1, then xh remains in this ellipsoid for all k, delta and d in d gamma. This result is proved using the S procedure. A natural question pops up. How do we solve the shown inequality? First, we note that in IQC problems, the filter Psi is fixed a priori and the matrix S is kept as a variable. Thus, the variable tau2 is lumped with the variables in S. This is possible since the variables in S appear linearly and since delta also satisfies the pointwise IQC defined by Psi and tau2S for all tau2 non-negative. Second, the theorem requires the inequality to hold for all d hat and gamma. This introduces an infinite number of constraints in the theorem. However, if the shown inequality is imposed, then it becomes sufficient to impose the inequality in theorem 1 at the vertices of the polytope gamma. The only remaining problem is the multiplication between tau1 and P. This nonlinearity is resolved by gridding over tau1 and solving a convex optimization problem at each grid point. We now consider a simple illustrative example. Let the matrices of system G be as shown and assume that delta is the set of static linear time varying operators that represent the multiplication in the time domain by a time varying scalar delta k between -1 and 1 for all k. This set delta satisfies the pointwise IQC defined by Psi and S shown on the slide. We note that the filter Psi is a static operator, which implies that xh is equal to xg. In this example, the set gamma is taken as the interval -1, 1. Thus, by imposing the previously mentioned constraint and by further leveraging the symmetry of the set gamma, the inequality in theorem 1 needs to be imposed only at the vertex d hat 1 equal to 1. We seek the minimum volume invariant ellipsoid by minimizing the log determinant of P inverse. The value of tau1 equal to 0.56 gives the smallest objective function value. To illustrate the invariance of the computed ellipsoid for this value of tau1, we perform two sets of simulations on the uncertain system. First, we consider randomly generated delta k and dk values. Second, we set both equal to 1 for all time steps k. In all the simulations, the initial condition xg0 is randomly generated on the boundary of the ellipsoid EP. But what if the filter Psi is dynamic? Theorem 2 introduces an additional positive definite matrix Q and a non-negative scalar tau3 such that the shown constraint holds, where E satisfies the highlighted equation. Theorem 2 allows us to conclude that if xh0 is in the ellipsoid EP, then xhk is in the ellipsoid EP for all k, delta, and d as per theorem 1. Furthermore, xgk is always in the ellipsoid EQ defined by the matrix Q. In addition, since the filter Psi starts from a zero initial condition, then requiring xh0 to be in the ellipsoid EP is the same as requiring xg0 to be in the ellipsoid defined by P11, the 1-1 block of P. This allows us to strengthen the conclusion of theorem 2 as shown. As argued in the paper, the variable tau3 can be set equal to 1. This leaves us with determining the matrix Q. In fact, it is desirable to have Q equal to P11, as in this case, the ellipsoid EQ becomes an invariant set for xg. For P11 to be equal to Q, P has to be block diagonal, and thus we simply need to solve the inequality in theorem 1 for a block diagonal matrix P. However, if imposing this block diagonal structure renders the problem infeasible, then a method is proposed to approximate the condition P11 equal to Q. Let us now consider a second illustrative example where the nominal system matrices are defined as shown and the uncertainty set delta is the set of static LTI operators that represent the multiplication in the time domain by an uncertain parameter delta whose absolute value is less than or equal to alpha. This set delta satisfies the pointwise Iqc defined by the shown Psi and S. In this case, we note that Psi is a dynamic Iqc filter. The set gamma is taken as the set of vectors in R2 whose components are between -0.5 and 0.5, and thus can be expressed as the convex hull of its vertices d hat 1 through d hat 4. In this example, we solve for a block diagonal positive definite matrix P that satisfies the inequality in Theorem 1. Tau 1 equal to 0.935 gives the minimum volume ellipsoid EQ. We demonstrate the invariance of the computed ellipsoids EP and EQ by considering two sets of simulations, where in case 1, the parameter delta and disturbance inputs are randomly generated, and in case 2, they are chosen to be fixed. In all the simulations, the initial condition xg0 is randomly generated on the boundary of EQ, and xc0 is set equal to 0. In conclusion, we have derived results that combine Iqc tools with the S procedure to compute ellipsoidal invariant sets for uncertain systems. The proposed approach requires solving a non-convex problem, which is handled by solving a grid of convex optimization problems. Future work include applying the proposed approach to a practical example and addressing the nonlinearity in a more systematic way. Thank you for listening. The floor is now open for questions.